this core, or trying to detect disks that would be of the order of, before we started all this investigation, mostly people were saying disks are around a few hundred AUs in radius. These were the typical disks we knew 15 years ago. So we had already a hint that this was not the case. We had made a survey in 2010 showing that this is data on the left-hand side, showing the emission from the dust at very small scales around 2 young protostars, and we were arguing that this data is not compatible with models of the formation of large disks that you see on the right-hand side, that were predicted by just hydrodynamical collapse of cores that would produce very naturally large centrifugal radii, because a lot of angular momentum was included in these cores and had to be conserved. So we went for Calypso, which was a large program, to try to find these small disks, whether they were small or large, and how the angular momentum problem was being solved during that phase. Was it by the formation of a large disk, or do we have to find another option? What we found can be summarized in this plot. Of course, Calypso did many other things, but I'm going to focus here on what we did for disks. So what we found is that, as you can see on the right-hand side, most of the disks in the young protostar, class 0, class 1 protostar, are very small. If you add the literature of the time, so this was published 6 years ago, we were showing that more than 75% of the disks around class 0 protostar are smaller than 60 AU. This was what we could do with the surveys that were available at that time. So this was actually something that was a confirmation of what we had suggested in 2010, this time with... Sorry, I'm hearing someone. I mean, I'm not sure who is talking. So that the disks are present, but are quite small. And actually, this was confirmed by later ALMA surveys, like the Van Damme survey, that these disks are quite small, contrary to what is expected from hydrodynamical collapse that should conserve angular momentum, okay? So where are these large disks that should form if angular momentum is conserved during the collapse and during the formation of the star? And if it's not the disk that solves the angular momentum problem, but because we don't want to give it to the star, otherwise it rotates too fast and it just cannot sustain, where do we put it? So we try to measure rotation using Calypso in this course to try to measure the angular momentum in the core at the different scales. Okay, so this was an example of what we did in the paper from my PhD student in 2020. These are busy plots. On the left-hand side, what you see is the angle of rotation of the gas depending on the radius you look at in the core. And you see that if you normalize everything by the rotation at the small scale, which is basically at 100 AU here in this plot, you see that all these angles of rotation are completely randomized throughout the envelope. So the rotation is not a solid body rotation that is basically the same at all scales, first. And second, on the right-hand side, this is the specific angular momentum in function of radius in the core that we have measured. And you see that this is something that shows two slopes, a slope at very large scale, which is 1.6, which has been found by subsequent studies to be very similar, so 1.6, 1.8, which is very reminiscent of turbulent cascade and not rotation. Okay, so this would suggest that the motions that we probe at this 1000 AU scales and beyond may not be due to rotation, contrary to what we thought before, but mostly to turbulent motions in the outside of the core and in the surrounding ISM. And it's only at scales less than 1000 AU that you see a break in the slope, and actually something that is much shallower with a typical slope of around 0.3. So these protostars, not only they don't seem to have a lot of organized rotation motion, the velocity gradients are a bit all over the place, but for sure beyond 1000 AU there is no significant rotation. So we actually made models to try to reproduce what would happen if we were putting no rotation indeed at the large scale in these cores. And this is what I'm showing now on the left-hand side. These models show that we actually form disks. You don't need the core to be rotating like with solid body rotation at large scale when you start the collapse to form a disk. And we not only form disk, but you see on the right-hand side of the bottom panel, this is the angular momentum measured from the model, which has a value that is very similar to what we measure in the protostellar envelope. And this is without core rotation. So how come we have angular momentum without core rotation? It's because nature is not an isolated system. Cores are not an isolated system. And actually, the barycenter of the gravitational potential may not be the barycenter of the velocity field. And because of this, the referential are slightly different, and it's very easy to create local angular momentum. That is the reason why these disks are forming. So we think that with this data, we have a good hint that the formation of the disk is not a consequence of conservation of large-scale angular momentum, is more something local, probably within the 1000 AU, that is due to the motions at core scales. Another way to think about it is how now from this 1000 AU, how do we conserve this angular momentum within the inner envelope to form the disk? Is this something that happens? If I measure the angular momentum at 1000 AU, I will know the disk size because this material will conserve its angular momentum. Or is it something that is a bit more complex? And there is a phenomenon that is called magnetic braking, which is extremely important because at these scales, it can redistribute some of the angular momentum. This is well known. And actually, it has been shown by analytical models, but also numerical models. I'm showing you here two of the ones that are made by my collaborator, Patrick and Bell, showing that if you include magnetic field during the collapse, naturally, you will produce much smaller disks. So this is the analytical formula here. You see that there is an order of magnitude between the disk that you would form with ambipolar diffusion and magnetic field, 18 AU with a dependency on the magnetic field, the ambipolar diffusion, and the mass, while the hydrodynamical case would be basically 100 AU with a dependency on the mass and on the density. So this is really key. On the right-hand side, you see also how putting different magnetic field and different configuration of magnetic field. So the angle that is indicated is the angle between the magnetic field axis and the rotation axis of the core. And you see that when the magnetic field is strong, mu equals 2, for example, and the magnetic field and the rotation axis are very well aligned, you form very, very tiny disks. Magnetic braking is super efficient. If you put an angle, mu equals 2, angle of 40, this is the bottom one, your disk is slightly larger. If you put less magnetic field, mu equals 5, your disk is larger, and so on and so forth. So there is really a key ingredient here for the disk formation, which is the magnetic field. And at that point, when we published the Calypso results, we had not really very good idea of what the magnetic field was doing dynamically at this small scale. So this is why we went with this project to measure the magnetic field. And I'm going to show you a few results. There are many more groups that are doing this kind of studies with very interesting results. I just picked here a few things. So the project was called Magnetic Waiezos. This is something that was running between 2015 and 2020. And we have been using dust polarization to trace the magnetic field in this object. This is something that is well known from the ISM, okay? This is a Planck map showing that the dust polarization can be used to trace the magnetic field. I'm not going to explain everything. I think you have several experts in the room who can explain to you much better than I do why the dust grains are aligning with magnetic field lines. What we know is that from these Planck maps, if you go down in these two cores, SVS13, L1448 in Perseus, you see that the magnetic field still seems to be relatively organized at the parsec scales from this Planck data. The question now is if I go inside the core, is it still the case? Is the magnetic field still organized? Is it becoming a mess? Is it dynamically relevant? Is it able to break the material and set the disk size? So there were many, many ALMA results recently trying to follow what's going on using dust polarization. These are a few examples. And what we can say is that from ALMA data and our data that we got also in my collaborations, B fields are detected everywhere. This is something that I think no one will argue. When we look for the magnetic field in a protostellar core using polarized dust emission, we always find it, okay? So there is no good evidence that some of these cores are completely devoid of magnetic field. First. Second, when you look at LOMA scores, we find relatively organized B fields, okay? We don't find completely turbulent kind of B field lines that would go all over the place and that would reduce a lot also the polarization fraction because of cancellation. No, we find relatively high polarization fractions and relatively organized B fields in these LOMA scores. In massive cores, it may be less true, but this is not my main research. So with the SMA, we had, before ALMA, we had already started to gather data to try to make a survey of these LOMA scores. This was published, and then our idea was to test whether we were finding this correlation between the angle of the magnetic field at core scales, okay, this is very important, and the rotation axis would lead to reduced rotation if the two are very well aligned, as was suggested by the models. So this is a gallery of the protostar we have surveyed. This is the dust continuum emission. The outflow axis is used as a proxy for the rotation axis. And we have measured the mean magnetic field at core scale. Once again, this is the red segment that you see on these maps. And we have tried to see if there was a correlation between the angle between the rotation axis and the magnetic field measured at these scales, 2000 AU, and over properties of the core. And we found one. We found one that actually was also found by a more recent ALMA survey published by Bo Huang in Orion. So this was the first time that this was observed with our data, and I think now this correlation has been robustly proven. What do we find? We find, as you can see on the right-hand side, that the more misaligned is the B field with the rotation axis, so this is the misalignment that we are tracing in the x-axis, the more misaligned, the larger the kinetic energy in the core is found. Okay, so this velocity gradient is a velocity gradient that is measured in the equatorial plane that is supposed to be sensitive to rotation mostly. And you see that the objects that have a lot of misalignment at core scale, once again, I want to be very clear, 2000 AU, you shouldn't go at 10,000 AU, you shouldn't go at 200 AU, you should go at a scale where the magnetic field can break. So we know that this is in the inner envelope, but not at the disk scale where you start to have a lot of effect from the outflow and everything. So this is really, from the models, there is a sweet spot. This is where you have to measure these things. So what this suggests is that the objects that have misaligned magnetic field are rotating less at 2000 AU, which is an indirect potential signature of magnetic braking. Another thing that we find, but that is very tentative and I think needs to be explored much more, is the color of this object. We find that more objects are in multiple systems, in systems where the magnetic field is misaligned, also a signature of magnetic braking, okay? So this was really like a pilot survey that I think now will probably make much bigger statistically relevant results with new data. Hopefully people will do this. So we have been comparing our data of the polarized dust emission with magnetized model of star formation, at least in a few objects, to be able to have a more detailed, basically, explanation and interpretation of our data. So we used Ramses models, MHD models of the formation of solar type cores. And we have processed them with the Polaris tool that was written by Stefan Reissel, using typical dust and basically doing all the radiative transfer with RAT alignments, the radiative torque alignment with the magnetic field. And then we have put this into an ALMA simulator to check against our data, for example. So I'm showing you here a statistical study we done looking at 54 models where we have tried to understand. So the big map that you see here, these are the different models, okay, seen with different orientations. And basically the fact that you see almost nothing is rather good news, because you don't see nothing when what you measure with the polarization angle is a good measurement of the magnetic field line direction, okay? This is the error you make to measure magnetic field line direction when you use in this object dust polarized emission as a proxy. These objects are complex, they drive outflows, they have disks, they are optically fixed. So it was very important that in these conditions, we make a good assumption whether polarized dust emission is really a good tracer of the integrated magnetic field topology. And this study showed us that we could be quite confident as long as we don't go to high frequencies where things become a bit difficult with opacity effects. Valentin Le Gouellec also has been looking at our data and trying to all the ALMA data, actually took all the ALMA data in polarization, and he measured the efficiency of dust alignments in these objects. This is something that you can basically measure by comparing the fraction of polarization and the dispersion of the polarization angle. I invite you to read this paper if you want to know more. And what we have found is that in protostars, there is an increase of efficiency of dust alignment compared to the diffuse ISM. All the points at a given polarization fraction are above what you would find in the Planck ISM. So this would mean that dust is aligning very efficiently in this object with some even potential extra power of alignment compared to the diffuse ISM. So this also tells us that we can trust the dust alignment to probe the magnetic fields. And we have used this in an object that is called B335. I will go very quickly on this because I think it's some old result and mostly people know it already. So it's a single object where we had made an ALMA map of the dust polarized emissions. This is what you see on the left-hand side, and we have compared it to an MHD model to see whether we could reproduce the velocity field and the dust polarized emission, to the magnetic field topology, considering either strong braking or weak braking. This is an object where the disk size is known to be very small by several ALMA studies. So we have shown that the only way to reproduce these parameters in this object was to take a model with rather high magnetic fields. So it's not super high, it's mu equals 6. So mass to flux ratio equals 6. So you form an object, no problem, gravity is winning. But the magnetic braking is strong enough that you are removing a lot of angular momentum during the collapse, and you'd form only this very small disk size. One thing in this model that was surprising is how coupled the field has to be. As you see here, what we see is from an initial magnetic field orientation along the outflow axis, so where you see these red-blue arrows, we have created an extremely pinched magnetic field in the equatorial plane. That really shows that the material, while unfolding, has been pulling the field with it like very efficiently, with very few somehow, and bipolar diffusion to release a bit the field. So we have a very, very pinched magnetic field configuration in this object, which was a bit surprising in our models, we needed to basically have non-ideal MHD, but with very strong coupling. And this was explained maybe by some subsequent measurement we made in this object that was showing that there is actually a very high ionization fraction in the center of this protostar, contrary to what is expected by models where cosmic rays have to go through the core to ionize. If you take these models, this is what is shown on the right-hand side. These are the models in gray. You see that most models, the cosmic rays don't penetrate the very high density. So they don't manage to produce high ionization rates in the very dense part of the core. So here, the ionization rate that we measure in this object, the only way to explain it is that cosmic rays are being produced by the protostar itself. And maybe the ionization in the center is high and that we are back in a more ideal MHD. So the field is very well coupled. And as a result, indeed, we have this very strong pinching and this very, very small disk. So all this kind of tells a story that seems consistent. The thing is that if these objects are producing cosmic rays, is it all the time? Is it episodic? Do we have like ideal MHD and non-ideal MHD oscillating? This is really the question. Note that this source had an outburst before we observed it. So this may be also linked to this very high cosmic ray production. Okay, so if I'm not incorrect, I still have something like 5 minutes, so I will go very quickly through the last part so that we have time for questions. So while we were actually using the dust emission, and especially the dust polarized emission, to try to trace the magnetic field in these objects, we found out something really weird with the dust. And this is why we decided to go on and try to understand a bit better what was the nature of the dust in these objects. So first, you all know, dust evolves. Otherwise, we will not be on this little rock orbiting a star. I mean, we need to form planets. Planets are everywhere. So we know that at least some of them are rocky. So the dust from the ISM, which is less than a tenth of a micron, has to be able during the star formation process to form objects that are thousands of kilometers. Okay, so you need to find a very efficient process sometime that allows you to accumulate the dust from the very small dust to form planets. So this is clear. Until very recently, people were looking at protoplanetary disks, where we were thinking, okay, this is where you do all the dust evolution. I mean, you take a disk that is full of ISM dust, and because of the disk pressure conditions and so on, you will form dust trap, you will form planets, and the dust will evolve in these Titori disks. What we found with our polarized dust emission is that it might start a bit earlier. So we have two different pieces of evidence for this. These are the two plots I'm showing here. On the left-hand side, you have the dust emissivity. So it's not polarized emission, it's dust thermal emission. So we have measured the dust emissivity in a sample of our Calypso objects. So it's the slope of the dust emission in the millimeter. And what you see in this plot that I'm showing is that all our objects show dust emissivity smaller than what is measured in the diffuse ISM. And in the state of the art of our current dust models, which we need to revise, by the way, only large dust can produce such small emissivity. First point. So in the envelopes at 500 AU, dust emissivity should be characteristic of millimeter dust grains, which is huge. Second point is on the right-hand side, comes from the polarization this time. Same thing, you take your models, you align your dust with the local radiation field that you know is correct for the luminosity of the protostar, and you produce these curves of polarization fraction in function of radius in the envelope. And you see that these curves that are very low polarization fraction compared to the value that are actually observed, which is the gray box. So it means that you align much more efficiently your dust grains in these environments. And there are two ways. Either your dust is very different from what you assume, or you have much larger dust grains, because only large dust grains will align very efficiently with millimeter photons that are typical of these conditions. So this was very surprising because no dust model tells you that you should have very large grains in such young objects. I mean, you would need, in theory, millions of years to form these large grains and not on 10,000 years. So we have been, I'm going to go a bit faster. So we have been thinking, okay, there is clearly this star formation phase that has not been explored in terms of dust, and that we need to characterize a bit better, because this is when you form the disk. So the material you put in the disk will come from these envelopes. So more recently with Luca Cacciapuoti, we have been confirming this in one protostar that we have studied with 5 ALMA bands, that the dust emissivity has to be much lower than in the surrounding ISM. So this is L1527. And we are now developing models of big dust aggregates for the dense medium, which are currently lacking, and showing that indeed, if you focus only on the one that is circled in red here, that the typical values that we are observing can only be reproduced so far with large dust grains, with dust grains that are around 50 micron in size. So we need to develop more models, because what we also are doing is varying the fraction of carbon in these grains, which is key to drive the dust emissivity. But at the same point, we want to keep high polarization fraction. So we have all these constraints that we need to fit at the same time. For sure, I'm just going to, well, I'm going to skip the ash fall. I think we have good observational evidence of this, but this is a different story. And just to finish, I wanted to say that, yeah, we are now being able to develop MHD models with dust evolution during the MHD evolution of the core. So this is what you are seeing here in this slide. This is an MHD model of two solar mass core collapsing to form a star. And you see that in the envelope, this is the two distribution you see on the right-hand side. You have the initial mass distribution in black and the mass distribution after 10,000 years of evolution in blue. In the envelope, just by collision of grains, we are already able to form 10 micron grains, okay? So this is something that is absolutely surprising. And this is also because of the MHD, so ask me questions if you have. Okay, I leave you with my conclusions and I'm happy to take questions. I cannot hear nothing.
Well, Anna, I have a question. I have a comment.
Okay, well, Thiem, I think you are muted. I don't hear anything from the room, but please, Anne, go ahead.
Okay, just to tell you that I am very, very enthusiastic about all you have presented. And I remember a very old paper we did with the old Plateau de Bure interferometer when Frédéric Guth was a student. So it was a paper from '96 where we found that in the central part of the flat of the pseudo disk, if you want, of L1557, we found that the beta was characteristic of grain growth, and at that time nobody believed us.
Yeah. Well, I feel you because at the time I said the disc were super small, nobody believed me, and now nobody believes me either. So I know this paper, I think actually, and there was also some weird beta, I think, in the outflow cavity walls that where was some emission. Yeah. So I know this paper indeed, and I think this was indeed some first clue that something was going on, and we need now. I mean, we need to understand better because there are temperature effects that are a bit nasty. So that's why it's important to have very good models. But indeed, I mean, yeah.
Maybe another comment. Can I do another comment? Okay, you mentioned very something that for the moment ALMA has not yet investigated very deeply, is that most of the protoplanetary disks we observe are large, bright disks. But we know that there is a huge amount of stars, of Tetori stars with very small disks. Even new stars are at the same age, between 3 and 5 million years. So then the question is this because they formed or had initially a different magnetic field? Because we do not know what happens with this population, why they are so different.
Yes, I agree with you. So, I mean, indeed, I know that the most recent surveys of large surveys with ALMA have found that actually most of the T-Tauri disks are small.
Yes, exactly. But
And
you know, this was something claimed by Thierry Monmerle a long time ago.
yes. No, but I think indeed, I mean, we are just re-exploring things that some people maybe said at some point, most of the time, and then we are trying to make it stronger. But indeed, so this is also, I think it makes sense. I mean, because most of the young disks are very small. So, and we don't think that viscous evolution is actually very likely to affect a lot the dust. Okay, so for the gas, it's going to be a bit different, but for the dust, if the disk is formed small, it's going to be difficult to expand it later. So I would think that this population of small T-Tauri disk is the natural outcome of the fact that most disks are born small.
Yeah, and it has implication for planet formation then.
Yes. I agree. I think the conditions in these very small compact disks are probably quite different. And that's why it's so important to study them. And so I fully agree with you that if this is something that is being found also now in the more evolved object. I think we were biased by the beasts before, by the very large disks that we were able to study before ALMA, which were the largest ones. And now we are finding all these small ones, which are probably the most typical ones for planet formation, indeed. So we need to understand how it affects our scenario. I fully agree. Yes.
Thank you for your nice and for your answer.
So Tim, please go ahead.
Okay, yeah, so now can you hear me?
I can hear you from far away, but I'm going to try.
Okay, okay, good. So I have two questions. So
Yeah.
first of all, here your results suggest that larger grains, more than 10 micron grains, are present in the protostellar envelopes. So does it imply that the effect of dust on ambipolar diffusion is less important, or what?
Yes, you are correct. So I didn't touch on this because, well, you cannot do everything in half an hour. But indeed, if dust is growing already during the first phases, and if it doesn't refragment, which is another question. So if you remove the small grains, you will indeed remove most of the coupling in these conditions between the material and the magnetic field, because these small grains are the ones that are carrying the charges.
Yes.
Okay, it's just a question of volume. And so basically, if you remove these small grains to make bigger grains, your magnetic field will be you have ambipolar diffusion that will be completely affected. And so this is something that has been shown actually by models, that if you remove the small grains, you go back to forming large disks.
Yeah, I see. Okay. So now I have one more one comment. So you mentioned that the projection fraction in protostellar environments is higher than the ISM, and you concluded that the alignment is different from ISM dust. But I think that there's another reason is maybe there's evolution in grain shape. So grains are more elongated in the protostellar environment, so it can also produce higher population fraction.
Absolutely. So this is something I know that you have been working recently on this. This is something that we have not tested yet with our data, and that we should definitely do. But I agree with you that if for some reason in these environments, when you grow the grains, you make them more asymmetrical, which I think some of your work has been showing, then you would be able to increase the polarization fraction. I think still, if you only have 0.1 micron grain in an envelope where there is no 0.1 micron photon, you need big grains to make polarization.
Micron grains cannot reproduce such a high population. You need larger grains. But I mean, at the same time, large grains, you also need like elongation grains.
Yes, absolutely. So I think you need, because you want to have grains that are of the order of the wavelengths, this is the key. And because in these environments, your photons are mostly in the submillimeter, you have no optical or UV photons. If they are completely absorbed within the first 10 AU, at 500 AU, you have none left. So you need larger grains, and of course the polarization fraction can be increased if they are on top of that more elongated. So it doesn't mean that you need a huge fraction of these large grains. Maybe a smaller fraction of very elongated already.
Yeah, right. Yeah.
So this is something that we need to investigate, and I hope we will be doing this.
So Zhang is currently modeling the grain growth with the increase in elongation. So hopefully we can have a more self-consistent modeling about dust evolution.
I look forward.
Thank you.
Okay, so thank you, Anael, for very nice talk and discussions.
Yes, okay. So let me.
So you hear me?
Yes.
So we move to the next review talk given by the Dr. Andrew Choi from the University of Bordeaux. She's going to talk about the protoplanetary disk property derived from the recent millimeter and infrared observation. So please go ahead, and you have the 40 minutes.
Yes, 1 minute, because I cannot stop the sharing right now because I lost my mouse, so Anne can share.
We see the Anne's screen already here.
Ah, really? Okay, I still see my own screen, so this is a problem. Okay, fine, go ahead.
So you see my screen. Okay. Good morning, everybody. Sorry, good afternoon. So I recognize the nice, I see the Quinion room. After this very nice introduction, okay, Anael did a very nice introduction for my talk. So on my side, I will focus on the class 2 object, protoplanetary disks, and I will mostly present some recent result derived from millimeter and submillimeter observations. So I will not introduce a lot, not discuss a lot. I will just make a brief introduction explaining the astrophysical context, and I will focus particularly on low mass and intermediate mass pre-main sequence star of between 0.3 to 2.5 solar mass. And as we discussed already, is that I will focus on results coming from large disk and some warm disk, in particularly disk orbiting around Herbig star. Do you see my mouse?
Yes, we do.
Okay, so I can use it. Okay, and then to describe these physical properties, I will mostly discuss the gas properties. I will also present some recent results from MAPS project or from EXO-ALMA. And I will spend some time to discuss the specific case of edge-on disk, which allow us to retrieve both the radial and vertical distribution. And I would like to convince you that then with new ALMA observation, you have the way to really understand the temperature profile in this disk, but also to start to understand better the problem of the disk mass and the turbulence, for example. If we want to think about chemistry, I think it's more complex. And then I will focus during the last minutes about planet formation and how we can be sure that we see a planet embedded in a gas-rich disk, such as these Tetori disks. And you will see that it is not so simple. So first of all, just to go one step further than what we discussed previously, when I said previously, here you have the fraction of infrared excess versus age in several clusters. And what you see, in fact, is that you have a steep decrease, and the typical mean lifetime of protoplanetary disks, it's about the same for the gas and the dust, is between 3 and 5 million years. So this means that, of course, we have some older disks, but not so many. So it makes strong constraint on the time needed to form, for example, a Jupiter planet. So we have to keep that in mind, is that everything is, we have, this also means that at 5 million years, we have about half of the stars, or the pre-main sequence star, we have, which has almost no disk. Okay. So then when you look with this, so here you have a sketch from 2010. So it's relatively old, but I like it because you see half a disk and you see here the disk which is flaring. It's a balance between gravitation and gas pressure. And what the disk is illuminated by the stellar, by the stars. And then you have a very cold midplane where most of the molecules are stuck onto grains. So then you have a rich molecular layer. When I say rich, I would say more or less rich because we do not detect so many species. And then you have the surface, which is like a PDR. So in terms of chemistry. And of course, with ALMA, you are able to study the outer part of this disk. And if you want to focus on the inner disk, then you have to go to infrared and optical. Okay. So what we see here is that then we have a relatively strong vertical and radial gradient, both in gas and, in dust, in density and in temperature. So I like this very recent sketch from Karineberg et al. 2023, because it illustrates very well the disk complexity. So I will not discuss all these processes, chemical and physical processes during my talk. I just want to tell you that finally a disk is a kind of condensate of all the chemical and physical complexity that you find in the interstellar medium. You have grain growth, you have dust settling, you have PDR at the disk surface, you have a very dense and cold region like dense core at the midplane, so it's very complex. Well, now the question is, what can we today investigate and really measure with derived from millimeter observation? So First, very important result is that if you look at that, then as I told you, the molecular layer is at the intermediate scale between 1 to 3 scale 8. And I think a very important result coming from ALMA, it's relatively old, more than 10 years, is this observation of HD 163296, which is an Herbig star. So we have a warm, large disk. These are 12CO322 observation, and you see here channel maps. And when you compare with just isovelocity lines, a very simple model of a disk which is inclined along the line of sight, what you see here, it is a systemic velocity, and then you see the red and the blue and red-shifted part that you see here, okay, on both sides. So, okay, that's a disk in Keplerian rotation. But while looking at more carefully, you see a kind of phantom image, okay? What is it? In fact, you have to keep in mind that we have the molecular layer, which is at a very well-defined altitude. So it's here CO is freeze out, here CO is photodissociated, and you have the molecular layer. So this is Z, this is R, so this is half of a disk. So you have the second molecular layer of the other side of the disk below, and this is exactly what you see. So I think this observation, since we have enough sensitivity and resolution, thanks to ALMA, it was, I think, the first clear demonstration that we have a CO molecular layer. And in fact, if you look at the location of VCO vertical layer based on very simple models, this is a model of a flat disk, CO everywhere, so similar to this one. And here, this is a near cone, and you see this is slightly shifted, and this is a far cone, and this is shifted in the other side. So then at the end, this is what you see. And from this observation, they resolve the two 12CO molecular layers above and below the midplane with a difference of about 15 degrees. Okay, but of course, to do that, you need high spatial and spectral resolution. Okay. Then going to go further, the question is you have to analyze better this, to understand the disk physics. One very interesting point is that the first molecular transition of CO221, CO322 are thermalized and optically thin at the condition we observe in this disk. So then this means that we can try to derive the thermal structure from these optically thick and thermalized lines. So here you have some very important results from the MAPS project. At least for me, these are the 5 disks which were observed by MAPS. So what you see here, these are the CO, all the CO lines, 12CO, 13CO, and C18O. And Charles Lelot and collaborators, then from this data, from the channel maps and taking into account the Keplerian velocity, retrieve the location of the vertical layer of CO. And what they found is here, this is typically the vertical location in HIM-LOPI of the CO221 of the CO221 and 322, which is between 2 and 3 scale 8, while the 13CO 221 emission, 13CO being of course optically thinner, so it's you see deeper inside the disk, and then they see the layer below, and then they compare that with a very simple empirical model of temperature, which was in fact originally developed by Emmanuel Dartois when he was postdoc at IRAM with me. So using that, and they found, okay, then by this way, the vertical stratification of the temperature. Then the second analysis of this data by Zhang et al. 2021, always in the context of the MAPS results, was using a very complex, more complex thermochemical model to retrieve the CO from the CO distribution to retrieve the temperature of the gas temperature of the disk. And by this way, they found that in fact, the empirical measurement and the current thermochemical models can provide a reliable temperature structure in the range of 1540 K. So I think this result is one of the more important results from MAPS, at least for me, because this means that we start to quantitatively measure a very basic but fundamental parameter, which is a thermal profile. But you see that in fact, for 5 objects, they need to have 6 maps, CO, 12CO, C18O, and then this means that at least 2 ALMA transits, so it's very, very time consuming. Another point which is very important, mentioned also by Anaël of the case of class 0 and class 1, it's the disk mass measurement. So here, based on you have a plot from a review by Anna Miotello et al. 2023, where they present the disk mass, all the recent disk mass measurement obtained in TW Hydra. So using TW Hydra is very interesting because it is a closer Tetori disk, 56%. So then it's easier to see it. And you see, in fact, that based on the various methods, both from the dust continuum or from multiple studies of molecular lines, you have a huge dispersion. In fact, larger than the 2 magnitudes in difference. So this means that if we want to understand to measure properly disk mass measurement, we need to compare all these methods together. And now I would like to present still an emanation of a MAPS project, which is by Schwarz et al. 2021, where they used all the existing CO data in the ALMA archive, including MAPS data, plus the HD emission observed with HD 120 emission observed with Herschel. So they model this very carefully using a thermochemical model, the same than for Zhang et al. 2021. And by this way, they were able to measure, to estimate, okay, the gas and the dust mass. And they were very surprised because GM Auriga is a disk of about is a star of about 1.1 solar mass, and they found 0.2 solar mass. So then they did Toumre analysis, and they found that might be at least partly unstable. But well, that's a way to measure the disk mass, but we do not have so many HD observation. So, and you see that in that case, again, it requests lots of observation, so it's time consuming. Then from I invite you to have a look, because in the ADS archive, because end of April, there was 17 papers based on the last large program from ALMA, which is ExoALMA. And here I will present only one result from this survey, which I think is very important because it is a new method to measure the stellar and particularly the disk mass. And this is in fact based on the modeling of the rotation curve of an inclined disk, taking properly into account the vertical and radial temperature gradient. And we did that in all the sources of the survey, and they were able to derive the disk mass. And they also done some study of the Toumre criteria. They found that in that case, all sources are gravitationally stable. They also compared with recent measurement, mostly from ALMA, but using several techniques. And they found relatively correct and good agreement. The interest of this method is that, okay, you need to have an accurate measurement of the thermal structure, but it is independent from disk chemistry and composition, and you do not need to make a very complex study of the chemistry. Okay, or partial study of the chemistry. So I think it is a very promising technique, but of course it works for angularly resolved disks. Okay, another important physical parameters relevant of protoplanetary disk is the turbulence. And in fact, thanks to ALMA, we are able to get some measurement of the turbulence. So here the idea is to study the amplitude of the local velocity fluctuation. So, okay, you have the thermal term plus a turbulent term. And if you use several lines, having different opacities along the line of sight. If you reconstruct the model, the global model of the disk, we should be able, in theory, to measure the turbulent term. So this is what is done here, again in HD 163296, because it is a big and warm disk, so relatively easy to observe. And this is here what was found, for example, for C18221, CO322. These are the location of the emitting layers around, okay, so around an opacity of 1. And what from that and from other studies on DMTO, MWAC, and V4046 in Sagittarius, so there are not so many measurements because they are time consuming. The conclusion is that the turbulence is subsonic and a small fraction, in fact, of the sound speed. Okay, but I think this part, there are a lot of work still to do with ALMA. But again, as you can see, for this purpose, you need really to understand the thermal structure. But I think in the next year, we should have a more turbulent analysis. And in fact, maybe we may be able to have a 2D mapping of the turbulence. Okay, now I discuss what we can get from inclined disk. I would like to discuss more what we can see with edge-on-disk. So the interest of having edge-on-disk is that you see the vertical and the radial structure. Okay, and thanks to the fact that these disks are in Keplerian rotation, in fact, we found in 2017, we've shown that a straight line in the position velocity diagram, a straight line, like for example this one, correspond to the very well-defined radius. So then you average along that the emission along that radius, along each radius. You can do that at all the altitude above the midplane you want. You do that everywhere. And then by this way, you are able to retrieve the brightness, the radial and vertical brightness distribution. Moreover, if you observe a line which is optically thick, like for example, enthermalized like CO221 or CO120, you are able to measure directly the kinetic temperature. And here, what you see is that in fact, if you look at Z equal to 0, this is the location of the inner radius, and you see that with the altitude, its location is slightly changing. In fact, what you see here by this, it's just directly, because you are looking directly looking at various altitude, you are just looking, in fact, the flaring of the disk. So it's a very powerful method. And here, these are the first results of this new method, where in 2017, we published a paper based on ALMA observation at 0.5 arc-second resolution or 60 AU in linear distance, where we were able to retrieve the brightness distribution of CO221 and of CS524. And you clearly see that, in fact, the CO is tracing the whole emission, while CS is more located closer to the midplane, but we were not able to go farther than that because we were strongly lacking of vertical angular resolution. Okay, but the point which is very good is that if you have enough angular resolution, you should be then able to directly compare with chemical model. Okay, so now if we compare what we can get from edge-on-disk with inclined disk, these are again from Low et al. 2021. It is a plot showing the individual measurement of the disk surface, emitting surface in CO221. And then you see that then they used several methods to try to improve the signal-to-noise ratio. But you see then by this way is relatively uncertain on the vertical location of the observed molecular layer, which is not the case, of course, for an edge-on-disk as soon as you have enough vertical angular resolution. Okay. And in fact, this is a direct proof of what I am saying. These are flying saucer observation at 0.5 arc-second with ALMA. And these are recent observations of the same disk at 0.18 arcsecond, still with ALMA. There are 2 papers submitted on this. And what you see, what you see here, it is a CO221 for the old data, and this is the CO221 for the new data. And you clearly see at that time the location of the molecular layer. And for the 13CO, you clearly see that it's slightly inner in terms of location. So then we are able to see really the vertical stratification of the molecule. And then from Dutré et al. 2017, we did a modeling based on Wien observation and tried to measure the vertical temperature gradient. And I will show you now our prediction for 0.3 and 0.1 arcsecond resolution. They are here. So then, when you look at that, from this relatively low moderate angular resolution, we were able to produce a model which is not too bad compared to the new observation. So our modeling was interesting. One point, the fact that we see differences here and here is due to the fact that the disk is not fully at 90 degrees, but 87. So just a small impact of the inclination. And well, okay, so that's very nice that we were able to predict that. Then the question is, why do you need more observation if you can produce so nice model? And the question is, in fact, planet formation. If we want to understand planet formation, we need to characterize the midplane. And if you look at here, it's a kind of gray area. We do not know from this observation what happens in the midplane. While on the new observation, we clearly see that we have CO depletion, and it's also see in 13CO221. So then we really need to have high angular resolution. And from this EdgeOn study, I think we will be able to measure really the physical and molecular properties and chemical properties of the disk stratification, of the disk vertical structure. So please stay tuned. There are 2 papers which are just submitted. Okay, another work still on EdgeOn disk is by Coralie Fouché, who is my student. Okay, so the flying saucer was a 0.6 solar mass. The SSTO O4 2021 is a 0.3 solar mass. So then it's a very, very, well, it's relatively very low mass star. And there is a paper submitted. So she also applied the tomography on all the observation from the ALMA archive that you see here, CO221, CO322, 13CO221, C18021, and then also HCO plus 322 observation from NOEMA. So NOEMA was able to observe with an angular resolution, which is about the same than ALMA. So she applied she minimized the data in the UV plane using our model, which is called DISFIT, using this kind of parametrization for the vertical temperature gradient. And here you have the tomography of the observation, you have the tomography of the best model, and you have the results. So for this observation, we were clearly able to clearly see a well-defined molecular layer. We got direct temperature measurement with an upper layer, which is at about 30 K, a molecular layer of about 70 K, and a midplane, which is also derived from the dust and CO at about 10 K. A very interesting point is that the HCO plus 322 is thermalized, and then we are able to determine an estimate of the local density inside the molecular layer around 1 and 200 AU. So please stay tuned also, because we have also a new NOEMA observation on a few molecules. And then the next step of this observation will be to get a coherent modeling of the vertical structure in order to try to derive properly the density of the disk, in particularly in the molecular layer and maybe in the midplane. Okay, so really, if you want to study EdgeOn disk, the next step for me is a molecular study is observing EdgeOn disk. As soon as you accept to spend enough time to get the proper sensitivity for this purpose, because if you want to do it properly, you typically need to have between, let's say, 8 hours of in average for a single observation with ALMA. Okay, now I will move to my last part of the talk, which is toward planet formation. And first of all, we know that we have indirect tracers of planet formation since many years. Here I have chosen to present the SEED survey from Subaru, where you see that you have spirals, you have gaps, and in many objects. Another example here is MWC758. You have this very nice observation from SPHERE with a simple model of linear perturbation or linear spiral waves. So you see here, then you should expect to have 2 planets here. And this is a model from Dong et al. 2015 based on SPH simulation that you see. In fact, it might be related, these spirals might be related to planet inside the disk. Okay, here I present an image of result from Fuong that we did together in 2020, we published in 2020. And you see here spirals revealed in CO gas inside the large disk of Gegето. And in fact, the more convincing spiral, the brighter one, seems to originate from a hotspot CO hotspot we detect a few years ago and using ALMA, and which is likely an accreting planet. So then it's hot because it is accreting. And you see clearly the spirals. The other planets are more putative. So you clearly see that then you observe spirals both in dust and in CO line. Okay, another example is Abe Origa. These are the Tang et al. 2017 paper based on ALMA observation of CO221, where you see this nice spiral detected inside the cavity of the Abe Origa disk. So Abe Origa is a Herbig star, so it's a massive, large disk. And here you have the dust ring still shown with ALMA. And when we observe it with SPHERE, Anthony Boccaletti and collaborators were able to also see this kind of spiral. And since the observation were done 4 years, there were 4 years in between, we see that in fact, we seen that the location of the hotspot seen in CO, the bright spot seen in scattered light emission, okay, is rotating in the right direction expected from a Keplerian speed. So it might be related to an embedded planet here. Okay, more recently, okay, there is also a possible Jupiter-like planet observed by Curie et al. 2022, but and which would be located at about here, explaining. Okay, but I will come back on this later. So in fact, that's a way. We have rings, we have gaps, and we have spirals. Another indirect way to observe a possible embedded planet is to search for velocity kink inside the channel maps of the CO emission of the disk. You have here an example from Pent et al. 2018. So you see here what you expect if you have a perfect Keplerian disk. And you see here, contrary to that, a channel where you have a kind of you have a kink. In fact, it might be explained by a planet located here in that case. In fact, there are many kinks detected in this in different sources. So this is from Pint et al. 2023 from PP7 chapter review 18. But there are also new EXO-ALMA results where they got 5 new cases. But one point is sure is that we observe a lot of kinks, but only a few are in fact related to planet. So here you have an example is that if you assume that you have a self-gravitating disk, then you also can observe locally such a kink. So this is another way, but it's not, finally, it's an indirect way, which is, again, not 100% robust. So then, what is robust? So then if you want to observe a planet, you expect to have a circumplanetary disk around the embedded planet. So maybe directly searching for the CP disk is the best. And in fact, it was very successful in PDS-70. So here you have the sphere observation and the millimeter ALMA observation. And they found, for example, this object here and this object here. But well, the problem is that it is only in PDS-70 that it is so clear. In fact, for example, we search for CP disk using ALMA observation in the case of Abe Auriga cavity, because Tang et al. 2017 found, in fact, that we had an extended millimeter emission. And when you look at the residual, we may have something, but it is a paper which is still in preparation, but it is not so easy. So my impression is that this method is very useful and very efficient when in fact there are no residual of gas and dust inside the cavity. So maybe because PDS-70 is slightly more evolved than the Abe Auriga system. Okay, another way, which is interesting, then going to the CPD, is to say, okay, these are accretion disks. So then we search for shock tracers, either in the millimeter range or in the optical. So here you have two examples. This is from the review from PP7 review from Curie et al. 2023. So these are the PDS-70, where you see Muse result with H-alpha observation. So you see, in fact, this one is also detected in millimeter, as I told you. So you see H-alpha emission, which is point-like. But here, for example, in the case of Abe Auriga, this emission is extended, and it is not clear to understand the origin of this emission. There are controversies. Okay, another way is to observe SO, because SO is a shock tracer in interstellar medium. And based on a reanalysis of all ALMA archive in SO around Abe Auriga, we were able to find, in fact, this is a ring emission in SO. And here we have a very slight excess of emission in the red wing, which is in fact corresponding to this image. So this is the image of the ring. And then it might be here, this is a location of the putative planet detected by Tang et al. With indirectly detected. So it might be related to an accretion shock due to the surrounding material onto a young planet. Okay, but the resolution is low and it's very difficult to firmly conclude from this observation. However, there are similar observations with ALMA on a few objects. It might be for the next few years an efficient way to search for embedded planet in objects where there are still material around. But again, it is time consuming, so it is difficult. And then now I think I will conclude. Thanks to ALMA, we provide high sensitivity and resolving power. I think we are unveiling the 2D protoplanetary disk structure, particularly for large and intermediate scale structure. Inclined disk is based on inclined disk observation, but there are limitations on the vertical location of molecule. However, the thermal structure, I think, is really better known now. And we have a detailed study of the kinematics, which allow more accurate determination of masses, both disk and stellar mass. I think the next step is to understand fully the 2D structure for the dust and for the gas in terms of vertical and radial distribution. And for this purpose, edge-on disk are really the sites where it has to be done. And it will be, I think, the first real beginning of understanding the chemistry, because you will be able to say, where is the molecular layer? What do we observe in the midplane where planet form? Okay, well, coming back to planet, I think we have a lot of sign of departure from symmetry in most disks, rings, gaps, spirals, warps. But it is not clear. I think everybody agrees that not all of them are linked to embedded protoplanets. Coming to protoplanet detection, they are, for me, the convincing case of PDS-70, which is the only really convincing case. Maybe because the cavity is just clean, because it's slightly older. But using accretion shocks may be a promising technique, even it is time consuming to observe this object. And but one point is clear is that only one evidence is not enough. We need to have several indirect proofs to be sure that we observe an embedded protoplanet. And then I would like to give you a message for coming home. Do not hesitate to investigate the ALMA archive, because I think there are many interesting results which are still waiting inside, for example, as the SO observation in Abe Auriga. So thanks a lot, and I will stop there.
Okay.
Oh, I was a little bit too long, sorry.
Thank you very much, Anne, for a nice and informative talk. So we move to the Q&A section. Is there any question from audience? Is a question from the...
Yes,
Hi, Anne.
hello.
Yeah, I'm happy that you are still very active. Thanks a lot for a nice review. I have a small request that can you update me on the how do we understand the problem on the inner cavity? We find that it's too big for some disk, like
Okay,
in
inner
the
cavity.
digital.
Okay,
Yeah.
okay. Inner cavity in disks. So that might be due to photo evaporation, but many of them may be due also to embedded planets, and in some cases, I think even for more than one embedded planet, particularly those where you observe spirals and so on. But the point is that since these cavities are not free of, most of them are not free of gas and dust, I think it's very, very difficult to understand what happens. The best example is Abe Auriga. You see here that in fact the inner cavity in optical is very, very near infrared here, is very complex. So if you want to understand what happens inside, it's not easy.
Yeah, another question.
Yeah, thank you very much, Anne. It's Thiam speaking. I have one question about the turbulence that you measure. So you found that the turbulence here is subsonic, right? Subsonic
Yes.
turbulence. But I think some research refer to the turbulence mixing to explain the existence of large dust grains at high latitude in the disk, especially the existence of ice in this atmosphere. So I wonder what is the implication for it in terms of understanding why ice can exist on the surface of this,
Okay.
given the little turbulence here.
Okay, I think for me it's something which is open, because so far we have only a few measurements of the turbulence. It seems to be subsonic, but I think we need to. There are still a lot of rooms between the observation and I think the modeling, and this is
I see.
we need to adjust model in agreement with the observation, but in the meantime, we really need to have a kind of better understanding of the turbulence on a few objects.
I see. Okay, thank you.
I cannot tell you. That's it's still open.
Okay, yeah, thank you. I know.
Any other question?
Yes.
Yeah, is a question from Siwei.
Hi, I'm Siwei. I just a question about the flying saucer,
Yes.
the 12CO, 13CO, the intensity map, and you mentioned
The new data. Yeah, the new data.
yeah, you mentioned inclination angle is not exactly age on, but it seems like intensity distribution, I mean asymmetry, seems to be object in 12CO and 13CO. Am I right?
Yes, the 12CO and 13CO emission is optically thick and thermalized. Yes.
Right. So why the intensity contrast is object in these two lines?
I'm sorry, I'm not sure to understand your question. What do you mean?
Could you move to that slide of intensity map? Yeah, this one. So this
Yeah.
one 12 CO seems
One-
brighter in the upper part, but second CO seems to be brighter in the lower part.
Yeah, but okay, it's just a matter of inclination. When you look at a disc which is slightly inclined along the line of sight, and you do not enter exactly at the same location inside the disc on one side and another. This is an effect that we mentioned in already in the first paper. So this is just the reason. So here, this is a model obtained with 0.5 arc-second resolution. With a better resolution, you see you have this slight effect, but it's not bright. Okay, yeah, another point is that we may have some confusion with the molecular cloud. So for CO, it's slightly complex, but it follow, I would say it follow reasonably what we expect.
Okay, thanks.
Yeah, okay, so that is about time for break. So thank you, and again for very nice talk and the discussion.
Thank you. Have a nice afternoon and nice end of meeting.
Yeah.
Thanks for inviting me.
Yeah, bye-bye, see you. So it's time for coffee break and we will come back at, let me see. Yeah, 3:50. Yeah, we are 30 minutes of coffee break.